Alright, so our last keeper of this unit is 6.3. We have binomial and geometric random variables. Alright, now binomial and geometric random variables are just special types of random variables. The first one, your binomial, occurs when you have a situation where you either have a success or you have a failure. So either you got it or you didn't get it. In other words, if I was assessing the probability of flipping heads, or tails, well, if my variable is the number of times I flip heads, well, either I flipped the heads or I didn't flip a head. Alright, so I had either a success or a failure. There wasn't anything in between. Either I flipped it or I didn't flip it. Now, in order for you to have a binomial situation or a binomial setting, you have several things that you want to check. So the first thing you want to check is you want to make sure that the situation is actually binary. In other words, you have two outcomes, success or failure. The second thing you want to check is to see if it's independent. So you want to make sure that the actual trials themselves are independent. And I'll show you guys a way of actually figuring that out later. But you want to make sure they're independent of each other. You want to know the number of trials. Alright, so that has to be set up in advance. You can't just do it as you go. You need to know the set number of trials. Like, I'm going to do this 5 times. I'm going to flip the coin 5 times. That would be a set number of trials, 5. And then the last one, you want to know the probability of success. So like flipping a coin, the probability of getting heads is 50% or 0.5. So that's my probability of success. Now the way you want to remember this is through BINS, binary independent number success. And you'll check this for each situation that you feel in your heart is binomial, or if I tell you it's binomial, you'll check BINS first to ensure that it's actually binomial. Alright, so binomial random variable, again, this happens when you have a situation where you have two outcomes, success or failure. Your probability distribution is now called the binomial distribution. And it's basically the same exact thing. The only difference is you actually have a formula to figure out what your probability distribution or your binomial distribution is. Alright, so again, anytime that you have a situation that you believe is binomial, you have to check BINS. Alright, so again, that note is important. I'll probably write it down. And then also make sure that you're being asked to count the number of successes in a certain trial. So I want to know, like, the probability of getting 5 heads, blah, blah, blah. Like, they're actually asking you for the count of successes. Alright, so the formula for your binomial distribution is a little bit funky. So to start, now this is not the formula on this slide, but to start I want to give you like some old school math. So this notation that you guys see right here is called a combination. And you guys probably learned it back in the day when you did like combinations, permutations, the number of like ways you can, if you had 5 pairs of pants and 3 shoes, the number of outfits you can make or something like that. This is the formula that we'll use for that combination. Now this notation you probably haven't seen before. You probably saw it before as, and I'll just write it out because I want to make sure you understand it's the same thing. You probably saw NCR or NPR. That was a permutation. But this notation that you see right here, this is exactly the same notation where you have your total number of whatever you're looking for out of how many like groups you want. So I have a total number of 50 students and I want groups of 3, something like that. It would be 50 and then 3. And this is the actual formula. Remember that this little exclamation point, that's a factorial. So for instance, like 5 factorial, that's 5 times 4 times 3 times 2 times 1. And that's all that means, is your factorial symbol. And what's nice is your calculator actually has a button that will calculate your combination for you. If you go like to probability and then scroll down, or it might even be the first one, but it says NCR, and that's your combination formula. And it actually works this whole thing out for you so that you don't have to do it by hand. All right, so here's the actual binomial probability formula. So here we have the combination piece to it that I showed you on the last slide. So you figure out the combinations, and then you multiply it by the probability raised to the k. And k, again, is the number of successes that you want. So, and then you take the number of failures, which is 1 minus the probability, or the probability of failures, I should say, and raise it to the number of failures. All right, so again, this first piece is the number of arrangements we possibly have. This is the probability of success, p to the k, and this is the probability of failures, p to the n minus, or 1 minus p to the n minus k. Alright, so what's really nice about a binomial distribution is that it approximates normal, and because of that we can get formulas for the mean and the standard deviation. So for a binomial distribution, and I mean only for binomial, this only works for binomial, we can approximate the mean to be n times p and the standard deviation to be the square root of np 1 minus p. So that means the variance is just the square of the standard deviation, or np 1 minus p, which also comes in handy when you're working a problem. Sorry, this should be squared because it's the variance. Alright, so again, these formulas only work for binomial distributions, and they can't be used for any other distribution. Now again, we only, in this class, we only do two. We do binomial, we do geometric, but there are a number. You have the Poisson distribution, you have the gamma distributions, which is a whole family of distributions. You have like your exponential distribution. You have so many different types of distributions, but you want to remember that not all of them approximate normal, and even the ones that do approximate normal, they don't use these formulas. These formulas are very specific to your binomial distributions. Alright, so when you're checking your binomial setting, again, you check your bins. So first thing you're asking yourself, is it binary? Well, binary, that's just something that's given in the problem. Like, you need to understand, like, when you're reading the problem, it has to somehow indicate to you that you either have a success or a failure. So that's just something that you would state out in words. Yes, this is a binary situation because I either have a pet or I don't have a pet. I either flipped the heads or I didn't flip the heads. So you would state that in words. Now the second thing you check is your independence. Now a lot of times in the problem itself will say blah 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 is independent, or this independent variable, or whatever. It will say independent in the problem. But a lot of times it doesn't say it, and you have to assume. Well, assuming is fine as long as you're sampling without replacement. So for instance, if I sampled 50 students from Alatoona, all right, I did a random sample of 50 students. Well, in order for it to be a true, simple random sample, each student has to have the same probability of being selected. So technically, if I pick a student, let's say I pick Cameron. Cameron was my first student, and I picked him out. Well, now the other students that's left at the school have a better chance, and it's no longer a simple random sample. So in order to make sure that it's fair, I would technically have to put Cameron back in the pot. I'd have to put him back in the sample to make sure that now is, a valid simple random sample. Well, the issue comes in that, well, what if I pick Cameron again? If I pick him again, it's not independent anymore because Cameron's opinion for the first time I picked him and the second time I picked him is now overlapping, and now I don't have the independent situation or the independent characteristic. So basically, we have this rule that says if we have a sample size, if we have a simple random sample of size little n and a population size of big N, we can check for independence. Again, this is a check for independence. We can check for independence, and we can assume independence as long as your sample size is less than 1/10 of your population size. Another way you can see this is that 10 times your sample size is less than or equal to your population. Now again, if this condition is satisfied, we can assume independence even though we put Cameron back in the population. Even though we put him back in and we had the chance to sample him again, we can still assume independence using this method. Alright, so again, you want to be mindful if they're sampling and they're putting the person back into the population, you do have that chance to select them again. To ensure independence, you want to check that your sample size is less than 1/10 of your population. All right, so the next thing that we have to check for binomial, we did binary, we did independent. Now we want to check normal. Your normal checking is kind of hidden in this formula, but this is what you kind of want to highlight. To check for normal, you want to check to see that your n, or your sample size, times the probability is greater than or equal to 10. And then your n times your probability of, so this, okay, let me start over. This is your probability of success. So you're doing your sample size times the probability of success. You want to make sure that's greater than or equal to 10. And this is your sample size times the probability of, this would be failure, because it's 1 minus the probability of success. So this is sample size times the probability of failure. You want to make sure that's also greater than or equal to 10. So you want both your successes and your failures to be both greater than or equal to 10. If they satisfy this little condition, then we can say, okay, these things are normal. All right, so we did binary, we did independent, we did normal. Last thing, your success. Again, that's just like binary. It has to be said somewhere in the problem, or known. So for instance, if I'm flipping a coin, I don't have to spell out to you that it's 50%. You know that. But if I'm doing something like I'm asking people whether they have a pet or not, and I'm seeing, okay, whether or not you have 0 pets, 1 pet, 2 pet, or 3 pets, I don't know that probability off top. I don't know the probability that someone has 3 pets in their house. So that has to be given somewhere in the problem in order for you to identify success. All right, so that was it for binomial distributions. Now we're moving on to our geometric distributions, or geometric setting. A geometric setting basically occurs when you do something until it happens. So I'm going to flip this daggone coin until I get a heads. I'm going to ask neighbors whether or not they have a pet until I get someone that says they have 3 pets. All right, so that's your geometric setting. Again, it happens until, that's usually your key word. It's happening until something happens. All right, so you have, again, binary. Just like before, it's either yes or no. Either you have a pet or you don't have a pet. Either you flipped heads or you didn't flip heads. You have to have a binary situation. You want to, again, make sure that your trials are independent. We'll use the same rule. Either we'll say it, or n has to be less than or equal to 1/10 of your big N. You have your trials. Now this one's different, because remember, for your binary or binomial distributions, you had number. This one is trials. So you want to make sure that you actually have a number of trials, or you're looking for the number of trials until the first success occurs. So you want to, somehow in the problem, it has to say, I'm going to see blah blah, I want to know the probability, or I'm going to check the probability until someone walks through my door with a red shirt. Well, I'm doing it until the first success occurs. And then you also, again, need to know somewhere in that problem the probability of success. So to check for geometric, again, same thing like before, except for this time we're checking bits. Remember, binomial was bins, geometric is bits. Alright, so basically, again, if you have a geometric setting, we have a geometric random variable, and we can figure out the geometric distribution by actually figuring out the probability. And that's actually quite easy, because, for instance, let's say the probability of success, let's say that is 0.3. So that's the probability of success. Well, if I want to see the probability that I get that success, whatever I'm talking about, by the 3rd trial, well, that means I failed the first trial, so that has to be 0.7. I failed the 2nd trial, and then I got it on the 3rd trial, so I got a success here. Alright, so there are actual formulas, but that's pretty much what you do. Like, wherever they tell you you want to get that trial by, you do failure, 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 all the way up to right before that, and then you get your success on the very last one. So always be failure, 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 success, or however many you're counting. But again, you want to make sure you check bits first to make sure that it is actually a geometric situation. And that's it.